Good morning, y'all. So, hope y'all had a good holiday, good break. Hard to come back today. Just want to remind you that we have a quiz on Tuesday. That quiz will cover all of the chapter that we're on right now. Is that chapter 3, I think, the work, energy, and metabolism chapter. We should get pretty far in it today. We might not cover all of it today, but all of it will be on the quiz. Okay, so make sure you're reading that chapter. As I said, I'll try to take sort of big ideas from the chapter. So be looking for those big ideas. And then we'll probably have another quiz coming up. So we'll have a quiz here. We'll probably have another one around the 17th or 19th. That's the following week. And then we have our next exam on the 24th. And then that exam precedes the drop date for this class. So you should have a pretty good idea of where you are in that class. I don't expect y'all to drop. I don't think that we have anybody right now that's in danger of needing to drop. All right. So we talked about conservation of energy already. Do you remember conservation of energy when we were, that was like when we were talking about, you know, like if you have, say, a roller coaster, for example, where up here you would have lots of potential energy, but the kinetic energy would equal to 0. Let's see, what do we call it? We call it K and U, right? Is that right, what we've been calling it, K and U? Sorry, we call these things different things in my other classes. So where you would have lots of potential energy, but that your kinetic energy would be 0. And then down here, your potential energy would be equal to 0. Because remember, potential energy is dependent upon your height. How far away you are from the Earth, you'll have more potential for motion the farther away you are. And then our kinetic energy is dependent on the speed. So the faster you're going, then the more kinetic energy you have. And then at different places, you would have kinetic and potential that would both be bigger than 0. But the sum of all of these, U plus K, will always be constant. Okay? And we talked about that in terms of the book called it The Conservation of Mechanical Energy. Because our kinetic energy and our potential energy we call mechanical energy. But then they have another section that's just on conservation of energy, and it's really similar. I'm not really sure why they separate it, except that they want to talk about open and closed systems. So energy is conserved in a closed system, and in general we'll assume that all of the systems that we discuss are closed systems. And an open system means that energy or work can be transferred into the system. Means that you can give energy or you can do work on the system and change the total amount of energy that it has. And in a closed system, no energy or work enters or leaves the system. So in a closed system, and up here when we were talking about this, we were assuming that this was a closed system, so that the total amount of energy always remained the same. So in a closed system, the total energy remains the same for all the time. So U plus K will always be a constant value. It's not entirely true to say that this roller coaster is a closed system. Why? What are we discounting when we say that it's a closed system? How do you have energy leaving or entering the system? There are a couple of different ways that I can think of. Say with like a roller coaster. You ever been on a roller coaster? Yeah. My wife loves roller coasters. And I like them. Man, they're okay. But my kids, my son, not really a big fan of roller coasters. But we went to Six Flags a couple of years ago. And my wife was all excited. They had this pretty good, it was like an old wooden roller coaster. She wanted to ride it. And we got into Six Flags. We were like the first ones there. Nobody was there yet, and we raced to the back of Six Flags in St. Louis to hit the roller coaster, and we got our kids all excited about it, and so they were just sort of going along with the excitement, and then we get there, and we're the only ones on the roller coaster at the very front, right, because it was just sort of like the most exciting part to be in, and then we start moving, and my son's like, no, I don't want to go on the roller coaster. He was like, I don't know, 12 or whatever, 11 or 12. And there's like the entire roller coaster, he was freaking out about the roller coaster. But my wife got to go on it, she loved it. So where do you lose or gain energy in a roller coaster? Where do you gain energy in a roller coaster, first of all? How is this not a closed system? Where you gain energy? Going down, you transfer energy from potential to kinetic energy. So you're right, you go faster when you're going down, but you're not actually gaining energy. You're just transferring energy from one type to another. But where are you actually putting energy into the system? We're going up, right. So you're actually, because you got that chugga thing, right? That chain that pulls you up to the top of the hill. So that's one point where you're gaining energy. And then where's a point where you're losing energy in the system? Yeah, friction, which we could also just throw in wind resistance there too, right? Because wind resistance is really just a special type of friction. Okay, so in a closed system, our total energy will remain constant. Let's just make a note up here on this. Something that we had said was a closed system is not really a closed system, that you gain energy going up. That's like with the chain as it pulls you up the incline, and then you lose energy from friction, including air resistance. So even though we talk about it as a closed system, it's not exactly a closed system. If the system is not closed, then we can enlarge the system to include other parts so that the total energy does not change. What that means is, like, well, let's say with the roller coaster, if we include things like, say, the heating up of the rails, so as the roller coaster slides along the rails, it heats up the rails, that's due to the friction. If we included that type of energy, then that energy isn't exactly lost, right? That it's not energy that we're losing, that we're just accounting for it as some other type. Or if we include the electrical energy that's used to pull the chain, chugga, up to the top, then that's not energy that's actually entering the system, it's part of the system. So we can enlarge our system to include other types of energy that will make it now, where it was an open system before, now it becomes a closed system. And the book makes a point that as you get bigger and bigger, eventually your system will just consist of the entire universe, and the universe is thought to be closed. That means that there's no energy entering into the universe, and there's no energy leaving the universe. So the total amount of energy that's in the universe is what there is. And that's generally what's thought to be, that there is no incoming or outgoing energy. So your system, as you think of it getting bigger and bigger and bigger, eventually it will become a closed system. We'll think of the body as a closed system, more or less. Although obviously with the body, there's a lot of energy leaving the system. So you consume energy and you expend energy. We'll talk about that later when we get into the second section. So if a system is not closed, let's see. So a moving bicycle, it is not a closed system. Kinetic energy appears and causes the bike to move. However, if you include the man, it is closed. So this doesn't. I'll explain what it means in just a second. It is closed. The energy is converted from the man's muscles, which gain energy from the food we eat. Let me draw a picture to explain. So if we have a bicycle. Oh goodness, can I draw a bike? Yeah, that's pretty good, right? That's a pretty good bike. Yeah, so if I draw a bicycle, if the bike is moving, has a certain velocity, that bike has kinetic energy. But that's not a closed system because I'm having this energy just sort of appear, this kinetic energy that's entering into this system. And so if I think of this as a closed system, not a closed system, if I just look at the bike. But if I include the guy that's on the bike, or the woman, if I include the person that's on the bike, he's going to have really long arms. If I include the person that's on the bike, and then I take into account this entire thing, then that would be a closed system. Because the energy that's going into the bike is coming from the guy, and he's giving it this kinetic energy. I have this transfer of energy between these two objects, the bike and the person, and so I can think of the entire thing as a closed system. The universe is a closed system. No energy in, no energy out. Okay, you'll follow in the closed system. It really just means that no energy is going in, no energy is going out. Is that somewhat clear? Yeah? Okay. Power. Just need to know the definition for power. This will come up later, but it's the rate at which work is done. If it's a rate, then that should key you off that time is going to be involved here. Like we had a rate of fluid flow, remember that was like the volume per unit time. We had a rate of speed, that was a distance per unit time. So anytime we talk about a rate, we're always going to have some time, something over time. And so this is going to be the work over time. But remember that work and energy are closely related, and so I can also think of this as an energy per time too. And we'll just sort of use those to be the same as one another. So work over time or energy over time. I think on your equation sheet that the equation is listed as W over T for work over time. The unit for work is a joule per second, and that's equivalent to a watt, which is abbreviated with a capital W. Okay? Go down from here. Okay, so the efficiency describes how much energy is converted in a particular task. And the definition for efficiency, I think this is given in your equation sheet. We'll take a look and see. It is the power out over the power in. And because it's a percentage, in order to make that into a percentage, we have to multiply it times 100. That's just to make it into a percentage. So, for example, if I give, say, a power, if I get out of a system, I get a power of, say, 50 watts, but I've put in a power of 100 watts, then what's going to be my efficiency of that system? Huh? 50%, right, so it's just 50 over 100, that's a half, times 100, so that's equal to 50%. It just describes at some point, if I'm putting in 50 watts, 50 joules per second, or excuse me, I'm putting in 100 joules per second, but I'm only getting out 50 joules per second, then that must mean that I'm losing somewhere along the way that other 50 joules per second. So I'm only 50% efficient in this system. This can also be given in terms of work. Like here I give it in terms of power, but you can also think about it in terms of work. That the work output divided by the energy input times 100, that's equal to our efficiency. Let's take a look at the equation sheet. You can just stay where you are, but let's take a look there. I'll see how that is listed. Okay, yeah, I listed as power out over power in. But in a problem, if I gave you the work instead of the power, that'd be the same thing. Because remember, power is just energy or work over time. So when I divide power divided by power, the times just cancel out. And I just have my work out over my work in. Okay, where does, when you have a system, say in the human body, for example, the human body is not terribly efficient. But when you have a system like the human body, where does a lot of that lost energy go? Then I'm losing, say, 50% of my energy. Where does that energy go typically? Does it go into heat or sound or gravitational potential energy or kinetic energy? Where am I losing the energy mostly? I'm losing it mostly in the heat. In fact, the human body, we'll see later, is kind of like an infrared light bulb. It gives off a lot of heat. If you're sort of, you have a power rating basically of about 100 watts. Like a 100-watt light bulb, you give off about the same amount of heat. You ever been in a room with a 100-watt light bulb, like just you and the bulb? It can heat up a room pretty well. And so, like you heat up a room as well. All right, so most of that lost energy will go into heat. Let's try a couple of these clicker questions. An engine has an efficiency of 20%. It produces an output work of 20 joules. Then how much energy was lost? So first you need to figure out how much energy did you start with, and then you can figure out how much energy was lost. Let me pull up the clicker base. If I have an efficiency of 20% and I get an output work of 20 joules, what did I start with? That's the first question you need to ask. And then I'm asking here for how much energy was lost. So if I put in so many joules and I only get 20 joules out, then how much energy did I lose? Okay, about 6 of you, about half of you have it right now. Some of you, I think, are not doing the difference. So you're getting the first part of that question right. That is, how much energy did I start with? But then you're not figuring out what is the amount of energy that was lost. All right, let's stop in about 15 seconds. Stop at 150. Okay. And B is right. You lose 80 joules. So my efficiency is 20%. That's going to be output work. That's 20 joules divided by input work, which that's what I want to find, times 100, and that's equal to 20. And so now I want to solve this for Wn. So I would have 20 joules divided by Wn is equal to 0.2. And then I would solve it for Wn is 20 over 0.2, which is 100 joules. So the amount of work that I started with was 100 joules. And because I was 20% efficient, I only got 20 joules out of that work. Okay? Let me step through this again, what I did. But really, you should be able to, I'll give you pretty simple numbers. And so if you think about sort of how those numbers break down, then you should be able to do it without actually going through this algebraic step. So this is my equation. Work out over work in times 100 is equal to 20. And my work out over my work in times 100 is equal to 20. I divide both sides by 100, so I get 0.2. And then I I saw for Wn, that's going to be 20 divided by 0.2. You can cross multiply here and then divide both sides by 0.2. And then 20 divided by 0.2 is equal to 100. Okay, so I started with 100 joules, but I'm ending up with only 80 joules, or excuse me, with only 20 joules. And so that means that I've lost 80 joules. So to answer the last part of the question, I would say 100 minus 20 is equal to 80 joules. This was my initial energy. This was my final energy. And so I'm losing 80 joules. Practice these. You'll find that I do give you fairly simple numbers, so that I think that also if you think about the percentages, then you can reason out what the answer is without even having to do the algebra. But go through and practice some of these. We'll do a couple in a bit. Just practice them before the next exam. You'll probably see at least one of these where I ask you to find what is the efficiency of a system, or find what was the initial energy that was put into the system, or to find what is the energy that was lost. I would expect a question. Okay? You can do it, right? You can do it? Okay. All right. Where does the lost energy mostly go? All right, it goes into heat. So we just answered that out of circle A. Okay, so temperature and heat. I want you to be familiar with these three temperature scales. The book tells you how to go back and forth between them. I won't ask you to do that, but I do want you to be familiar with these three temperature scales and know what they're based on. The Fahrenheit scale. Fahrenheit is actually a German word. Fahrenheit. Fahren means like, I think it's dry, right? Anybody know German? Height is heat, I know. I think it's to drive heat. The Celsius scale. And then also the Kelvin scale. Kelvin is actually the SI unit. I know that you guys you rarely use Kelvin. Like you often use Fahrenheit, and I might use Celsius some, but Kelvin is the SI unit for temperature. So Fahrenheit and Celsius are really similar in the way that they're defined. And then Kelvin is quite a bit different. Fahrenheit is based on the freezing point and the boiling point of water. So for all the temperature scales, you have to set two temperatures that you know, and then you just assign some value to them. So for Fahrenheit and Celsius both, they take the temperature that water freezes and the water boils. And those are both our reference temperatures. And then you just say, okay, the freezing point is this, the boiling point is this, and that sets the scale for every other temperature. So the Fahrenheit scale, the freezing point of water is 212 degrees. The boiling point, the freezing point is 32. The boiling point is 212. And then for the Celsius scale, the freezing point, you know what the freezing point on Celsius is? It's a lot easier to remember. It's 0. And the boiling point is 100 degrees. I'm not sure where the freezing and boiling points on the Fahrenheit scale came from. You might know? Yeah, okay. So this just is a schematic of it. These are our freezing points at 0 and 32, and then our boiling points at 100 and 212. So once you set those two reference points with values, right, those are physical temperatures that you can measure, then that sets the number of degrees that you have in between. I do want you to recognize that there is a difference in the degrees, the size of the degrees. So let's do this as a clicker question. Which is bigger, a Celsius or a Fahrenheit degree? That is, if I have a change in temperature of 5 degrees, which one would be a bigger change in temperature? A change in temperature of 5 degrees Celsius or a change in temperature of 5 degrees Fahrenheit? All right, let's stop at 50. Okay, good. A is right. The Celsius degree is quite a lot bigger. And simply that I have 100 tick marks between the freezing and boiling points of water on the Celsius scale, and I have 180 tick marks between the freezing and boiling point on the Fahrenheit scale. So those Fahrenheit tick marks are just squished together a lot more just because I have more of them. I have 180 degrees between those, and I only have 100 degrees between that on the Celsius scale. All right. Don't need to know the numbers, 32, 212. Man, I don't really care if you know the numbers, but I will probably ask you a question about how they're different. And then also I'll probably ask you a question about on what they're based. The Fahrenheit and Celsius scales, they're based on the freezing and boiling points of water. Those are the two physical reference points on which those scales are referenced to. The Kelvin scale is a little bit different. Oh, let me just show you this. I'm not going to ask you to convert Fahrenheit to Celsius or Celsius to Fahrenheit. I'll do it here for you just so you see it, but I won't ask you that on the test. These equations are given in your book. I think they're on the equation sheet too. 9/5 of the Celsius temperature plus 32. And then my Celsius temperature is equal to 5/9 of TF minus 32. So if I want to convert 70 degrees Fahrenheit or 37 degrees Celsius, TC is my Celsius temperature, and TF is my Fahrenheit. If I want to convert 37 degrees Celsius, I would use this one. And so I would say 9/5 of 37 plus 32. And then that would be equal to 98 degrees, approximately. And then if I wanted to convert 70 degrees Fahrenheit, I would say 5/9 of 70 minus 32. And that would be equal to about 21 degrees Celsius. Okay? I'm not going to ask you to convert Fahrenheit or Celsius, but I want you to see this. What I will probably ask you is what are some common temperatures in the Celsius scale, because the rest of the world uses the Celsius scale, and it's just useful to know, hey, some common temperatures. So if you have, I don't know, European relatives and they tell you that it's 30 degrees outside, then you'll know that that's boiling hot, okay? So that's why I chose these temperatures, because the body temperature in Celsius, which is what, 98.6, right? Normal body temperature. In the Celsius scale, it's about 37 degrees Celsius. And room temperature, which is about 70 degrees Fahrenheit, is about 20 degrees Celsius. So I do want you to know just some typical temperatures. The temperature of the human body in Celsius, and then also the temperature of a nice day. A 70-degree day outside is about 20 degrees Celsius. Yeah. Yeah, it's just right here. Oh no, this has a little twiddly thing on it. It just means that it's approximately 98 degrees. But I'm not going to ask you to do that on the test, okay? Okay, so the Kelvin scale is a little bit different. You still have two reference points, right? For Celsius and Fahrenheit, those reference points were based on what? Man, y'all are amazing. The freezing and boiling points of water. But the Kelvin scale is a lot different. The Kelvin scale is based on absolute zero. And the triple point of water. So if I draw a thermometer like we had on the previous page, the Kelvin scale to start down here, which would have absolute 0. And we're going to call that T equals 0 Kelvin. At absolute 0, all molecular motion stops. When you have a material, a molecule, or an atom that is at absolute 0, everything in it stops. The electrons stop buzzing around the nucleus. They no longer move. You have nothing. There's no source of energy whatsoever. So absolute 0 is sort of a theoretical temperature, but you can't reach absolute 0. Remember the video I showed you with the liquid helium? Do you remember what happens to liquid helium when it gets close to absolute 0? What happens to a liquid when it becomes super cool? It loses something. It started with a V and then a Y. It lost all viscosity. So when a material like helium, liquid helium, which has a very, very low boiling point, so it boils at darn near close to absolute 0. When liquid helium becomes super cool, when it gets so close to absolute 0, it loses all viscosity. And that's why the liquid helium, if you recall, in that little glass container, it just slipped right through the confines of the container. It'd be like going to McDonald's and getting a drink, and it would just come out the bottom of the cup. Because, oh no, my Coke has 0 viscosity. And that means that it wouldn't interact with the sides of the cup at all. Like the cup's not even there. And it would just fall right out through the bottom of the cup. So if you ever go to a restaurant and that happens, you could say, it appears that my soda has no viscosity. And it's just all falling out the bottom of the cup. Or maybe you just had a hole in your cup. But anyway, it could be super cool. So at absolute 0, all motion stops. And of course you can't have that, right? Because they talked about in that video that in order to actually get something to absolute 0, that you have to have a temperature that's less than absolute 0. So that's what it means that that's a theoretical temperature. But nonetheless, that's one of our reference points for the Kelvin scale. And the other reference point is the triple point of water. The triple point of water is where water exists as a vapor, as a liquid, and as a solid all at the same time. As a vapor, liquid, and solid at the same time. It is about a temperature at about 0.01 degrees Celsius. So it's just above the freezing point of water, but it's also a particular pressure that allows the water to exist as a solid, a liquid, and a vapor all at the same time. Okay, so just know that the Kelvin scale is based on absolute 0. That's where all motion stops in a material. And the triple point of water, which is where the temperature where water exists as a vapor, liquid, and solid. Excuse me. The size of the Kelvin degree is the same as a Celsius degree. Okay, the Celsius degree is a lot bigger than a Fahrenheit degree, but it's the same as a Kelvin degree. Okay, don't need to know how to convert between scales, but I want you to know what the scales are based on. I want you to be able to identify the 3 scales: Celsius, Fahrenheit, Kelvin, and I want you to know some basic temperatures like room temperature and body temperature, 20 and 37 degrees Celsius. Okay, so let's look at heat. We cool on the temperatures? Ha ha ha. Did you get it? Very good. Heat is the transfer of thermal energy. So the total amount of energy inside an object depends on the type and amount of material. And this is called thermal energy. That's going to be different from heat. So thermal energy is not the same as heat. And when I talk about heat, they're related, but they're not the same. When I'm talking about heat, I'm talking about thermal energy moving from one place to another. And when I'm talking about thermal energy, I'm just saying, okay, there is so much thermal energy in this spot. But heat is all about the transfer. Thermal energy is just how much energy is in this object, but heat is the transfer of that thermal energy from one spot to another. If I'm going to have thermal contact, then two objects, if thermal contact is just the ability to transfer heat. So I can have thermal contact in a couple of different ways. One, I can just touch an object. If I touch an object, then I'm in thermal contact. Like right now, there's energy flowing between my hand and the desk. Which way is the energy flowing, by the way? If I have heat transferring between the desk and the hand, which way is it going? Is it going from my hand to the desk or the desk to my hand? Hand to the desk, right. So heat will always flow to a lower temperature. And so since the desk has a lower temperature than my hand, which is about, I don't know, 34 or so degrees Celsius, a little less than 37, then the heat will flow from my hand into the desk. You can also have thermal contact between two objects in a different way. Imagine if we have a fire. And then you have a person. You can be in thermal contact with a fire just by sticking your hand in the fire, which you shouldn't do, right? Like it's hot inside the fire, so don't do that. But you can also be in thermal contact with the fire if you put something in the fire, like say a metal stick. And the metal stick will cause energy to flow from the fire into your hand because the metal will heat up and it will transfer heat into your body. So there are two different ways to have thermal contact. You can touch an object or you can touch it indirectly with another object. So by direct contact, or by indirect contact. Either one of those are thermal contact. And thermal equilibrium is when there is no flow of heat between two objects. And this only occurs when you have the same temperature. All right, let's see, we're going to talk about changing phase here. When you have temperature that flows from one object to another, it'll cause them to change their temperature. But we'll also see that when you have heat flowing from one object to another, that can make it to change phase. So let's look at these phase change diagrams. You'll probably have one of these on the test. Phase change diagram. Not probably, you will have a phase change diagram. And I'll ask you to describe certain things about it. But first of all, there are three phases of matter. Solid, liquid, and gas. There is a fourth phase of matter. Do y'all know what it is? Don't write it down. Does anybody know? As I go from solid to a liquid, I heat it up and the molecules start moving around more. And so a liquid is just sort of more fluid. It can move around and move around objects. And then if I heat up the liquid even more, those molecules move farther apart and they're no longer touching. And that would be a gas. And a gas is compressible. It can fill a space. It fills a container. Well, what's the phase after a gas? Plasma. The plasma. And a plasma is just a gas that has been ionized. So you don't need to write it down. I'm not going to quiz you on it right now. But a plasma is just an ionized gas. Really hot things are plasmas, like the sun. The sun is like a big ball of plasma. There are other things that are plasmas too. Do you ever I know y'all don't go to these kinds of places, but those stores in the mall that sell all the really offensive stuff, what's it called? Spencer, yeah. Where they sell like the turd in a box kind of things. But they also sell those glass balls. Never seen one of those? That's a plasma. It's not hot like the sun. That gas is ionized in a different way through electrical energy. Fluorescent light bulbs, those have plasmas. They're ionized gases inside of them. Okay. Anyway, 3 different phases of matter. There is a 4th phase, but I won't ask you about it. Phase change just means when I go from a solid to a liquid to a gas, or in the opposite direction, I can go from a gas to a liquid to a solid. Over here on this top, don't worry about, this is a little bit more complicated than you really need to know. Don't worry about the enthalpy thing. We're not going to talk about that. But I just show this because you can go between these different phases of matter, that you can go from a solid to a liquid, either by freezing or melting. You can go from a liquid to a gas, either by vaporization or condensation. You can also go from a gas to a solid. That's sort of less common, but you can go from a gas to a solid, depending on the temperature. Yeah, you can go from a gas to a solid. And then you can also, if you ionize the gas, you can go into a plasma. Okay? Specific heat. This describes how much energy is required to change the temperature of an object. What do you think has a higher specific heat? You ever go to the beach? You ever been to the beach? Okay. Okay. So what do you think has a higher specific heat? Sand or water? Let's do this quicker question. Which has a higher specific heat? Sand or water? Think about your experience at the beach, because I know all of you have been to the beach. As you experience the beach and the water, which one do you think has a higher specific heat? That's what that is. Which one requires more energy to change its temperature? The sand or the water? Which has a higher specific heat? Well, come on, we're like half and half. Both of them are receiving the same amount of energy, right? Because what's their source of energy? What's the source of energy? The sun, right? The sun is available equally to the sand and the water. And so I want to know which one has the higher specific heat. Which one requires more energy to heat up? Okay, that's a little bit better. All right, I'm going to stop at 118. Okay, good. Y'all are sort of equally spread out. So the water requires more energy, right? Because I know that. Why do I know that at the beach? The sand is, I'm going to use her word, hot as hell. Is that what you said? Because the sand doesn't require much energy to heat up, right? That's why the sand gets so hot. But the water, on the other hand, water has a very high specific heat. The water requires a lot of energy to heat up. And you might say, well, that's the ocean just a lot bigger, doesn't it? Just require more energy just because it's so much bigger. But think about just, having a little puddle on the beach. Not much water there, but it still feels a lot cooler than that sand. The sand gets really, really hot. So the sand, huh? Okay. All right. So the sand has a much lower specific heat, or the water has a higher specific heat. Latent heat is the energy required to change phase. Phase. Like I'm going through a phase. And then calorimetry is a couple of things. The study, I'll go back to latent heat in just a second. The study of how energy if you've had Chem 105, y'all take Chem 105? You do? Good. So you talk about calorimetry. I'll remind you of the equations. There are two equations, Q equals MC delta T, and then Q is equal to the mass times the latent heat. This is our specific heat. You have these equations, they're on your equation sheet. You're not going to have to calculate anything with them, but you'll need to understand what they mean. This is our specific heat. Q is the heat. So the amount of thermal energy that's transferred. Remember, heat is the transfer of thermal energy. M is our mass. And delta T is just our change in temperature. So if I put a certain amount of heat into my sand from the sun, I have a certain amount of Q coming into my sand from the sun. This is the mass of the sand. This is the specific heat of the sand. Remember, the specific heat has a pretty small for sand, and that means that my temperature is going to be really big. So if I have a small specific heat, then my temperature is going to be really big. Whereas for water, I put the same amount of heat into my water from the sun. My specific heat is really big, so I have a really small change in temperature. Okay? So I'll be asking those sorts of questions regarding that equation on the test. This other equation is a similar thing, but this one is regarding to the latent heat. That's what this L is, the latent heat. And you might remember, or if you don't, I'll tell you right now, that there are actually two equations here. Q is equal to M times LV, and Q is equal to M times LF. Do you remember what the V and the F means? They're related to the changes between the phases. So what could the V mean if I'm talking about solids, liquids, and gases? It's vapor, right. So the V is for vaporization. So the LV is the latent heat of vaporization. It is the energy required. It's actually the energy per mass, but we'll just think of it as the energy to go from a liquid to a gas. Okay? If I have a liquid right here, I have to raise its temperature up to the boiling point of that liquid, whatever it is, before I can ever even think about changing it to a gas. But then I put additional energy into that liquid to break the bonds between the molecules that will make them go out into a vapor. There's a lot of energy that holds that liquid together. And I have to put in that amount of energy, the latent heat of vaporization, in order to make it into a vapor. Okay? Probably have a question about what is the latent heat of vaporization? It's just the energy, or really it's the energy per unit mass that's required to change a material from a liquid to a gas. In fact, let me correct that in my definition. It is the energy per mass. Okay? Required to change from a liquid to a gas. What's the F stand for? Huh? No, that's a good guess, but no, that's not it. It has to do with solids. You think of an F word that has to do with solids. I'm sorry, don't answer that. LF is the latent heat of fusion. And it's the same. It's the energy required, or the energy per mass, to change from a solid to or from a liquid to a solid, or vice versa, from a solid to a liquid. Okay, so those are just going between those two different phases of matter, from solid to a liquid, and then liquid to a gas. Solid to a liquid, that's fusion, and then liquid to a gas, that's vaporization. Let's look at this figure up here, because you'll probably have some question about this figure. I'll move up from here. I'll give you all a second. Oh. Okay, so this is a phase change diagram, and what it shows you on the y-axis is the temperature, and over here it shows the amount of energy. This is actually the amount of energy per unit mass. But the point is that down here, I'm putting energy. As I move from left to right, the amount of energy that I'm putting into this system is increasing. And then on the y-axis, as you might expect, as I put more energy in, my temperature increases. So in general, there's a trend moving upwards. As I add more energy to my system, say I have a pot on the stove, and I turn it on, I'm adding energy to that system, and it causes the temperature to increase. But something else also happens. As I put energy in here, I increase the temperature. And so if I wanted to know this, like how much energy was going in, what's my temperature change, this would be like my Q equals MC delta T. That as I put in a certain amount of heat, then it causes a change in temperature. But right here, this is where I'm changing phase. So I have ice now at 0 degrees Celsius. That's the freezing point of water. But it requires extra energy to change it into a liquid. And so this would be like my latent heat of fusion. Q is equal to M times LF. Here, I take that now 0 degrees Celsius water, and I raise its temperature as I add more and more energy. This is still our MC delta T. And then here, I have 100-degree water, but it's all water. As I add more and more energy, I convert that water into steam. And so this would be my MLV, my latent heat of vaporization. And then over here, I have 100-degree steam. And as I add more energy, its temperature only increases. So they talk about steam burns. Have you ever heard about, like, when you get burned by steam, that's can be a lot worse burn than if you get burned by, say, boiling water? Have you ever heard that? Yeah, because if you have 100-degree steam and 100-degree water, those two materials have a lot different amount of energy. The 100-degree steam has a lot more energy than the 100-degree water. And that's why a steam burn, if you're burned by steam, then it can just impart a lot more energy to your body than 100-degree water. Okay? So steam has a lot more energy than water because it has that latent heat of vaporization. We'll talk about this. This will become important in our AMP section because one of the ways that the body cools itself is through sweating. And sweating takes advantage of the incredibly high latent heat of vaporization that water has. And so if we put water in our skin and it evaporates, changes from a liquid to a vapor, it takes away that latent heat of vaporization from our body. And that's a lot of energy that it takes away. Okay, let's do a few questions. From old tests, we'll do the one on the left here. Fahrenheit scale is based on what? We'll stop at 38 or 40. That's if you don't know. Okay, very good. B is right. I want you all to get that right. You'll need to know the different reference points for the Fahrenheit, Celsius, and Kelvin scale. But the Fahrenheit scale is based on the freezing point and boiling point of water. The same is true for the Celsius scale. If it said Celsius, it would be exactly the same. If it said Kelvin, it would be absolute zero. And what else? The triple point of water. Right. So know those 3 different scales and their references. Hey, do you know what happens if you ever have and it's kind of personal, but if you ever have a bladder infection, you're in trouble. Okay, let's try the one here on the right. Which of these changes in temperature is smaller? A change in temperature of 1 degree Fahrenheit, 1 degree Celsius, 1 Kelvin, or do they all represent the same change in temperature? Which one's smaller? All right, let's stop at 55. 55. Okay, good. A is right. A change in temperature of 1 Fahrenheit. Remember, that's just based on how many degrees there are between those 2 reference points. For the Fahrenheit scale, there are 180 degrees between the boiling and freezing point of water. For the Celsius scale, there are only 100 degrees, so they're just spread out more. And the Kelvin scale is the same as the Celsius scale. Okay, what is the latent heat of fusion? Or what does it describe? All right, let's stop at 38. 38. Really, just 27 people in here? 7, 8, 10. Yeah. Where is everybody? We're missing well, all the important people obviously are here, but where are the less important people? That's what I want to know. They're sick? Oh, sleep. Yeah, I didn't want to get up this morning either. All right, so A is the right answer. It's the energy required for a solid to become a liquid. So if I'm thinking about this, I have gas, liquid, solid, and then I have these latent heats in between them. In between the gas and the liquid is my latent heat of vaporization, and in between my liquid and my solid is my latent heat of fusion. And I always remember vapor is a gas, and when I fuse something together, that means that I make it a solid. So fuse is like a solid. Which contains more energy? I had enthalpy here, but don't worry about that. I think your book talks about enthalpy, but I won't really use that word. But which contains more energy? Water at 100 degrees, steam at 100 degrees, or do both contain the same energy? All right, let's stop at 37. Okay, good. B is right. The steam at 100 degrees Celsius has more energy because, if I just think about this phase change diagram, the one that we drew on the previous page, that this energy is my latent heat of vaporization. The bigger diagram was on the previous page. When I go from, this is an ice, I add temperature to get it up to 0 degrees Celsius, and then I add heat to get it up to 0 degrees Celsius. Below here is like sub-zero ice. This is water and ice as I convert it from a solid to a liquid. And then I add more energy to get it to 100 degrees Celsius. And then once I get it up to 100 degrees Celsius, right here, I have to add additional energy to break those bonds between the liquid molecules and make them into gaseous molecules, to separate them. And so the steam has much more energy than the liquid at the same temperature. That's why steam burns are so dangerous. I want to play a clip for you. This is from an interview about a bomb calorimeter. I think it was on Science Friday, which is a radio show. Oh, where is it? Oh, there it is. Okay, so just a little bit about that. Just want to clarify some of the things that they said. With calorimetry, it's the study of how energy flows between different things. So our bomb calorimeter would look something like this. I would have a cup, an insulated cup, and inside of it, they put, this is where they had like their little fruit cake inside of it, and then it was filled up with water, and then they would have a thermometer that was inside the water to measure the change in temperature of the water. And then they explode what's inside of here, and it sort of becomes like the fuel for the fire. The fruitcake is the fuel. And depending on how hot the fruitcake burns, will raise the temperature of the water. So the fruitcake burns, and then the temperature of the water increases. You can measure that change in temperature of the water. The Q equals MC delta T. And whatever this is, whatever the energy that the water was required to increase in temperature, then that's the amount of energy that was in the fruitcake. Plus, they have to take out the energy of the other things that are inside of this little bomb because they put oxygen and other reactants inside of that. But it's a pretty simple way to measure the energy of food, and it's sort of the standard way for measuring that. No dietetics in here, right? Yeah? Okay. You ever talk about bomb calorimeters? Not yet. Maybe you will. I don't know. Okay. Let's look at heat flow. So there are 3 ways for heat flow to occur: conduction, convection, and radiation. I'm going to give you the definitions for convection and radiation first, and then we might come back to convection or conduction. So convection is requires the flow of a fluid. I'll give you the definition for conduction. It requires contact between 2 objects. So heat is conducted between those 2 objects. Convection requires the flow of a fluid, like for example a convection oven. Y'all know what's so special about a convection oven? Why is a convection oven different from just a regular oven? Which would be called, by the way, a radiation oven. We'll see that in a bit. Why is a convection oven different? What does a convection oven have that other ovens don't have? A what? They have a fluid, yeah. They have what?
Flow of air.
The flow of air. They have a fan. So a convection oven has a fan inside of them, or some way to cause the air inside of it to move around. And so not only do you have heat being transferred to the food by radiation, which is how a normal oven occurs, but you also have this air moving around, and that can increase the rate of energy transfer into your food, which can be good. So convection requires the flow of a fluid, and then radiation is the transfer of energy through light waves. And we'll have a whole chapter on light. When I say light, I don't mean just the light that you see, but there are all different kinds of light. We can call it radiation too if you like, and but it's just a particular kind of light. So you can have your convection oven, but then you can also have your radiation oven. And so I think that's what we should call our ovens from now on, because most of you have just regular old ovens, right? You have just regular ovens at home. So next time you use your oven, tell your friends that, hey, I'm going to go use my radiation oven, because that's really what it is. Okay? It sounds a little more ominous, though, than just an oven, right? But it's similar to a convection oven, except no fan. There's no flow of fluid inside. All right, let's talk about this conduction. I had a demo I want to do. I'll bring it next time, but I'll go and preface some of these things. There's a formula that describes the rate of conduction, like how we conduct energy. Looks like this: K A delta T over D. So each of these, K is our rate of thermal conductivity, or rather our thermal conductivity. A is our cross-sectional area. I'll just call it our area. T is our difference in temperature. I'm going to put a delta there. And D is the distance between the objects. So if I have two objects here and here, one has temperature T1, one has temperature T2. Let's say that T2 is bigger than T1, and they're connected by an object, say a metal rod. That's a metal rod. First of all, which way is energy going to be flowing in this system? From left to right or right to left? Right, it's going to be going from the hot thing, which is T2, to the cold thing, which is T1. So I'll have a flow of energy, Q, in that direction. Delta T is going to be T2 minus T1. It's just the difference in those two temperatures. The area is the cross-sectional area of the rod. So that's just the area. Just like looking on it at end, what is the area? I want you to notice that if A increases, if A goes up, then the rate of thermal conductivity is also going to go up. And that sort of makes sense, because if I make this bigger, then I just have more material for the energy to flow through. So if A goes up, then Q is going to go up. If that doesn't make sense, I can just look at the equation. If this value increases, then the rate of thermal conduction also increases. The energy per time increases. If I make my delta T bigger, if delta T goes up, then also Q over T will increase. The rate of thermal energy transfer will increase. If these two objects have a greater difference in temperature, then I'll have a greater flow of heat in order for them to reach that equilibrium temperature. And then also the distance between them. If D goes up, If I increase the length of that rod, then the Q over T will decrease. And I see that over here, that if this goes up, then this will go down. So I want you to understand those three relationships between the rate of thermal energy transfer, that's Q over T, and delta T, A, and D. But if you just look at the formula, there's no need to memorize those. You have the formula. Just look at the formula and you can see how they're related to one another. There is a fourth thing, and that's our rate of thermal conductivity. That's a constant. Another demo I want to show how that works. So we'll just do that on Tuesday. But remember, we're going to have a quiz on Tuesday. So when you come into class, we'll start with that quiz. It will cover, it's going to cover all of this chapter, all of chapter 3. This is chapter 3, all of chapter 3. I'll try to focus more on the physics portion, but you'll also see a few questions from the body portion. Energy about it. Okay, have a great day. Yeah. Not just the book, but have a good day. Have a good weekend.